So here I have a benzene ring, okay, bonded to a chlorine atom. My question is, does this chlorine atom, does it make the benzene ring more reactive or less reactive? So now what you have with chlorobenzene is this. Let's say that I am showing you guys this ring over here. Okay, this is the benzene ring. This is a benzene ring. Okay, then we're looking at it flat. Okay, so you can think of it as sort of lying in front of and behind the plane, right? And what you have over here is you have delocalized electrons over here, and you have delocalized electrons on top and bottom, right? So you have delocalized electrons above and below the ring, okay, below the carbon atoms. And this is bonded to a chlorine atom. Okay, this is bonded to a chlorine atom. Now, what you have here is now carbon के 2p electrons होते हैं, carbon के 2p orbitals होते हैं, right? The 2p orbitals on the carbon atoms are delocalized. The 2p orbitals on the carbon atom, right, are delocalized, or the electrons in the 2p orbitals are delocalized, right, like this, resulting in this giant sort of pi delocalized ring of electrons above and below the plane of the ring, right? On the other hand, when you have chlorine over here, chlorine has a 3p orbital. Chlorine has a 3p orbital over here, okay? Now, what happened in oxygen was, oxygen had a 2p orbital, what we saw in phenol. Oxygen had a 2p orbital, and that 2p orbital ke electrons delocalized into the ring very effectively. There was a very strong overlap, okay? And what happened was that even though oxygen was electron withdrawing, that overlap resulted in a large increase in electron density. Now over here again, chlorine is very electronegative, so it has a negative inductive effect. Okay? It's withdrawing electron density away from the ring. But at the same time, chlorine also has lone pairs, and one of those lone pairs, okay, is in a p orbital that's on the same plane as these p orbitals here. So there is also a resonance effect. Okay? There is also a resonance effect. Okay? But in this particular case, because the overlap isn't as much as you had in oxygen. Oxygen, because it had a 2p orbital, it had a much stronger overlap. These electrons were more delocalized in the ring than they are for chlorine, because it's the 3p orbital is much larger than the 2p orbitals. The degree of overlap is lesser for chlorine than it was for oxygen. So over here, the resonance effect isn't as strong as the inductive effect. So in this particular case, the negative inductive effect is the more dominant effect over here. So this actually makes chlorobenzene less reactive towards electrophiles. Okay, it makes it less reactive towards electrophiles. However, because of this resonance effect, it is just like phenols, it is also 2,4 directing. Okay, it is 2,4 directing, but it's not as reactive towards electrophiles. So as I mentioned before, usually what happens is the 2,4 directing groups are groups that are making benzene more reactive. Chlorobenzene is one of the exceptions. Okay, because it has this resonance effect, which makes it 2,4 directing. But the resonance effect isn't as strong as the negative inductive effect. In other words, chlorine actually withdraws more electron density due to its electronegativity than it donates due to the overlap of its 3p orbital with the delocalized ring, or due to the delocalization of its p electrons into the ring. Alright, it's less reactive towards electrophiles than benzene. Okay, chlorobenzene is less reactive towards electrophiles than benzene. In other words, it is a deactivating group. Even though it is 2,4 directing. Okay. Again, the negative inductive effect outweighs the resonance effect. For phenols, the resonance effect was much, much stronger because the 2p orbital overlapped much more effectively with the delocalized ring. Okay, so there was much more delocalization in phenols than there was much more comprehensive delocalization in phenols than you have in chlorobenzene. Okay, so here negative induction is it outweighs it outweighs the resonance effect. Okay, now let's actually think about the reactions of chlorobenzene. Okay, for chlorobenzene, okay, the reagents, okay, the reagents for electrophilic substitution are the same. The reagents for electrophilic substitution are the same. The reagents and conditions for electrophilic substitution are the same as benzene. Okay, but you would actually need to warm it a bit more. So for example, I'll give you an example. Let's say I start with chlorobenzene. Okay, and if I want to, let's say that I want alkylation to take place. Over here, right? So if I start with chlorobenzene and I'm trying to have alkylation take place over here, what I'm going to do is I'm going to have to heat it, okay, with AlCl3. So for example, if I say, let's say CH3Cl, right, and AlCl3, I will again have to heat it, okay, and what I will get is I will get this product here, okay. I'm going to get chlorine, and then how many possible products will I make over here? Considering that chlorobenzene is 2,4 directing, how many different products will I get if I'm carrying out alkylation of chlorobenzene? So again, my two possible products will be either the methyl group will go here, okay, and my other product that I will make in this reaction, I will again make a mixture of two isomers, right? The other isomer that I will make in this reaction is where the methyl group will go on the opposite carbon atom, okay? So it'll be either 1-chloro-2-methylbenzene or it'll be 1-chloro-4-methylbenzene. Okay, same thing for acylation, same thing for nitration. Okay, for acylation you'll use an acyl chloride and you're going to use AlCl3 and heat. For nitration you're going to use concentrated sulfuric acid and concentrated nitric acid. All right, and again the nitro group will either go here or it'll go here. Okay, so it's the same set of reactions towards both. So I'll just write this down, right? So for example, if I want to nitrate over here, right, and have the same thing. Nitration ke liye I will use concentrated nitric acid, concentrated sulfuric acid as my catalyst, and I will warm around 50 degrees Celsius, and I'm gonna get again chlorine, and then the nitro group will either go here, or my other possible product over here will be where the nitro group will go, okay, on the 4 position opposite the chlorine. And considering that chlorobenzene is a deactivating group, how would the rates of these reactions compare with benzene in the same conditions? How would the rates of these reactions compare with benzene in the same positions, in the same conditions? Again, same thing for acylation as well. We can add an acyl chloride over here. So let's say I'm doing CH3COCl, right? Then what will happen is, again, I'm going to use AlCl3 as my catalyst, and I'm going to heat it. And what I'm going to end up with over here is chlorine. And then now the acyl group can go on two different positions. It can either go on carbon number 2 or it can go on carbon number 4. Okay. But the rate of reaction, okay, assuming that these reactions are carried out, and let's say I'm reacting chlorobenzene with each of these, and I'm reacting benzene with each of these. The rate of reaction for benzene will actually be faster, or the rate of reaction for chlorine will actually be lower. Okay, we'll have a slower reaction take place with chlorobenzene because the benzene ring is actually less reactive The ring is less reactive towards electrophiles when chlorine is bonded to the it. Okay. So again, you have the same products here. And obviously यहाँ पर आपके बाय प्रोडक्ट्स, राइट, यहाँ पर आपका HCl बन रहा है, यहाँ पर भी आपका HCl बन रहा है, यहाँ पर आपका H2O बन रहा है. Okay. You can also add more halogens onto this. So if you use Br2 and AlBr3, right, then bromine atom आ जाएगा 2 या 4 position पे. If you use Cl2 and AlCl3 and heat, then chlorine atom एक और भी आ सकता है, and so on. Okay, so the same reactions, the same electrophilic substitution reaction that you had for benzene applied to chlorobenzene. Okay, but the difference is that substitution only takes place at the 2 or the 4 position. Okay, and the reaction is actually slower. Okay, the rate of reaction isn't as high because chlorobenzene is actually less reactive towards electrophiles than benzene is. All right, next we're going to look at the CCl bond in chlorobenzene. So again, let's say that I have this chlorobenzene over here, right? Let's say that I have this chlorobenzene over here, right? And I'll show the orbital overlap as well, the way we just drew it a few moments ago, right? You have this benzene ring. You have this benzene ring, right, with the delocalized electrons above and below it, and you have it bonded to a chlorine atom. You have it bonded to a chlorine atom over here, right? And chlorine atom ka jo orbital hai, 3p orbital, that's sort of overlapping with the ring, right? At the same time, chlorine is withdrawing electron density, and this withdrawal, so the lone pair on the chlorine atom is delocalizing into the ring. But in this case, the inductive effect or the electron withdrawing effect of chlorine is stronger than the degree of, or greater than the degree of overlap. Hence, the ring is less reactive towards electrophiles, right? And now I want to compare the CCl bond. I want to compare the CCl bond in chlorobenzene versus, let's say, a CCl bond in a regular, let's say, halogenoalkane. So let's say I'm looking at something like chloromethane. Where is the CCl bond stronger? Is the CCl bond stronger in chlorobenzene or weaker in chlorobenzene? So the CCl bond in chlorobenzene, okay, or the carbon chlorine bond is stronger than in halogenoalkanes. Okay, and the reason why is because the delocalization, okay, of the lone pair of electrons, right, in the p orbital, right, of the Cl atom results in an increase in electron density between the carbon and the chlorine atom, right? And if the electron density increases, that means that we have stronger electrostatic forces of attraction. Okay, between the nuclei and the shared pair of electrons, the shared electrons. Okay, so again, because of this delocalization, this greater electron density, which means that there's stronger electrostatic force of attraction between the nuclei of carbon and chlorine and the shared pair of electrons, or the electrons between the two atoms. So this covalent bond is stronger in chlorobenzene. The CCl bond is stronger in chlorobenzene than it is in something like chloromethane, which is a halogenoalkane, right? So what you have over here is basically this bond has partial pi bond characteristics, right? There's a sigma bond between the carbon and the chlorine atom, but you also have, you can think of it as like a partial pi bond because of the p orbital overlapping into the or delocalizing into the benzene ring. All right. So now if you guys remember in AS, we studied this reaction. We studied this reaction where if you took a halogenoalkane, let's take a halogenoalkane, okay, and we reacted it with NaOH aqueous, and we heated under reflux. What was this reaction called? This is called nucleophilic substitution, right? And specifically, if the Cl group was replaced by an OH group, what kind of a reaction was this? This reaction can also take place with water. What kind of a reaction was this? Nucleophilic. The mechanism was nucleophilic substitution, right? But what type of... This is called hydrolysis, right? So the mechanism was nucleophilic substitution, right? In this particular case, you have a primary halogenoalkane. Okay, so you would have SN2, a one-step reaction, right? You would have an SN2 reaction here. You would not have a carbocation. All right, no intermediate. It's a one-step reaction, and this was called a hydrolysis reaction. Now, considering that it's called hydrolysis because पानी के अंदर भी ये reaction हो सकता है, and what happens is that the CCl bond breaks. The CCl bond breaking by the action of water is hydrolysis, right? Now over here in chlorobenzene, the CCl bond is much stronger. So do you think it undergoes hydrolysis? In chlorobenzene, do you think the chlorobenzene undergoes hydrolysis the same way as a halogenoalkane would or a chloroalkane would? No, because the CCl bond is much stronger, right? It's relatively unreactive. It is relatively unreactive and cannot be hydrolyzed. It cannot be hydrolyzed like you would have in chloroalkanes. Okay, it cannot be hydrolyzed. So over here, if you try to react chlorobenzene, okay, with NaOH aqueous and heat under reflux, okay, no reaction would take place, okay, because this bond is much stronger. Iska hydrolysis cannot take place very readily. All right, so chlorobenzene does not react the same way as halogenoalkanes or chloroalkanes would. Okay, it does not undergo nucleophilic substitution, and it does not undergo hydrolysis because the CCl bond is much more unreactive. Okay, it doesn't break as easily.